Good afternoon, everyone. Welcome back from the spring break, and I hopefully you have had a good break. Before we start our class today, I want to make a reminder about our upcoming midterm 2. Okay, so it's going to be next week on Thursday. So I know original syllabus on the schedule says Tuesday, but it's now moved to Thursday. Okay, so make sure it's April 15th. Again, for 2 hours. You can take it any 2-hour period during that day. The content for this midterm is going to be conservation of energy, work, center of mass, conservation of momentum. So the chapter 7 to 9 in your OpenStack textbook. And also, if you look at our lecture notes, it's from lecture that we did on March 4th to the lecture on the 25th. So I did say center of mass, using the center of mass frame to solve conservation of momentum collision problems will not be on the test. Okay, so you don't need to learn how to use center of mass frame to solve collision problems, but the center of mass concept might still be included in the test area. Okay, I just want to clarify that. Format is similar as you had before, and you have a practice exam and a solution here, right here on Blackboard. So feel free to work it out, and I encourage you to do more practice when you have time to prepare. Okay. All right. So so that's all I want to say about our midterm. Are there any questions? All right, so if you think of any questions about the midterm, feel free to let me know. You can also email me if you think of your question later. Okay, so today we will start a new chapter called rotational motion. So far, all we've been discussing are translational motion. So what do I mean by translational? You're moving in this manner, right? Versus rotational, you're rotating, you're moving in this manner. So, but luckily, all we have learned from our translational motion, we can borrow it and using them as an analogy to learn these new concepts and new knowledge. Okay. All right, so I have, someone said they have a question about the new homework. So the homework question, we can't do that right now. So why don't you, you can either email it to me, your question regarding the homework, or you could come to office hours and we can work it out there, okay? So I want you to email it to me about the homework, okay? All right. Okay, so rotational motion, what we did with translational motion, we start with kinematics, right? Kinematics are where we talked about the position, velocity, acceleration. And we also find out the relationship between these different quantities, right? We derived 2 equations for constant acceleration. And we're going to use the same idea to do the rotational kinematics. Now, after we did rotational kinematics, we are going to do the rotational dynamics. So in the translational motion, we have Newton's second law, right? F equals ma. So we're going to use that as analogy to find, okay, so what kind of relationship can we have for rotational motion, for dynamics, right? So we're going to just follow that kind of strategy when learning new concepts. And also, like we have conservation of energy laws, here we will have a conservation of angular momentum. So following that logic, following that train of thought, I want to encourage you to always refer back to think about what we have already learned and how we can base our new knowledge upon that new information. So we start with angular kinematics, meaning that just like translational kinematics, we're dealing with position, we're dealing with velocity, we're dealing with acceleration. But now since it's rotational motion, we add an angular in front of everything. So instead of just saying position, we call it angular position. Instead of saying velocity, we say it's an angular velocity. Instead of saying acceleration, we say it is now an angular acceleration because it's a rotation instead of translation. Right, so translating is simply you're changing your position from one place to another. Now rotation is likewise. You can change your rotate position by rotating now, right? So you have a wheel, have this bicycle wheel, and any point on the wheel can change its position by rotating. So if you have gone 180 degrees, right? You have changed your position from here to here, right? If you have gone 360 degrees, then you have go all the way around and come back to the same position. So we need to define a quantity that can give us the angular position. So like any other, when we're dealing with position, we need to draw a coordinate system, right? We need an origin, we need an axis. So in this case, if you're looking at a bicycle wheel, we define the origin to be the center. So all the rotation are centered around that point, and you're rotating around this axis. You may have another different kind of rotation going on, and then you want to have to define a different origin and the axis. So I'm going to put a little table here, and we're going to keep adding back to our table our new knowledge as a comparison to the old knowledge, okay? So first, we are going to learn about position. In translational motion, we talked about position as represented by R, okay? And here we have angular position. So this is for translational. Here we have angular. Okay, so how do we represent position in terms of rotation? Yeah, I have already talked about, okay, so you said you would describe your motion by saying I have rotated for 90 degrees. I have rotated for 30 degrees. So the angle would be a measure of angular position, right? How much you have changed your, how much you have gone as opposed to the origin. So delta theta would be a measure of your angular displacement, the change in your position. So theta would be our angular position. Okay, so for some reason I could not, my pen would not write. Okay, so I will try to make my pen work and charge it up when you're looking at a clicker question. But for now, let's just look at my slide because I don't want to discontinue my screen share. Okay, so I'm going to use theta as a measure of my angular position. And the change of theta, which is delta theta, would be your angular displacement, right? As opposed to we have delta R for our translational displacement. So what are the units? Well, we can talk about the units using either degrees or radians. Or you can short it into just say RAD. You can say 360 degrees as is my entire change in my displacement, or you can say I have an angular displacement of 2 pi, which means you have go all the way around. Even though degrees or radians is a unit of measure, but it's dimensionless. It's not like meters, it's not like seconds, it's not like mass, kilograms. It doesn't really give you any dimension. It's a dimensionless quantity. Okay, so make sure when you are trying to figure out what the units, when you have the theta in your equation, try to remember that. And also, we said theta position is a vector, right? So when you have vectors, you can define something to be positive, something to be negative. Well, as a convention, we say counterclockwise is positive. It's just what people have decided to do, okay? So if you're rotating counterclockwise for 2 pi, then you'll say your displacement is 2 pi. Otherwise, you will say your displacement, if it's clockwise, is negative 2 pi. Okay, so that is position. Simply we use theta to represent it. Velocity is your next kinematics quantity. Again, let's recall how we define position in your translational motion. So we have the right velocity to be, the average velocity is change position over time, right? So it's delta R over delta T. So here you can replace delta R with its angular counterpart. So delta R becomes delta theta. So delta theta over delta T is the velocity in your rotational motion situation. So we call it angular velocity. And we use omega to represent this angular velocity. So omega average is the total change of your angular position over time, delta theta over delta t. Likewise, at this rotation, sometimes you rotate faster, sometimes you rotate a little bit slower. You want to be able to capture what is going on at the instant. You want to be able to capture what is going on in every little moment, right? So we have to take the instantaneous angular velocity, we define derivative theta over dt, d theta over dt as the instantaneous angular velocity, that is omega. You notice that I have a subscript z. Now this z is indicating the direction of the rotation. So z indicates that it's rotating in the counterclockwise direction, and we say the axis of rotation is in the z direction. Okay, so I talk a little bit more about how we define to be positive or negative in terms of the direction of the rotation later. Okay, so you can see we say omega is omega z, meaning that the axis of rotation is in the z direction. We are rotating in the x-y plane. Okay, so those are the two quantities we already decide. That is the angular position, theta, and angular velocity is theta over time, right? Change of theta over time. The third concept is acceleration. So how do we define acceleration in your translational case? Acceleration is defined to be what? Anybody still remember that? So how do we define acceleration for translational motion?
Change in velocity divided by change in time.
Yes, very good. Velocity over a period of time, change in velocity over change of time, excellent. So if you're looking at change of time overall, a delta t, and you get an average acceleration, which is delta v over delta t. So likewise, again, we do this analogy, delta v now becomes delta omega, right? Your velocity now becomes angular velocity, which is omega. So delta omega over delta t is your angular average angular acceleration. Again, your acceleration tells you how fast you're spinning up or slowing down. You could be having a very large angular acceleration, which means you're spinning up at a very high rate, or you can spinning up as a sort of a less a slower rate. So to capture what is going on in the moment, you need the instantaneous angular acceleration. So any guess what the instantaneous acceleration going to be? So alpha instantaneous angular acceleration is equal to what omega over t? Instead of delta, what do we write now? It would be d omega over dt. Very good. Excellent. You're taking the derivative with respect to time. Now, if you write it in terms of your position, then that's the second derivative of your position with respect to time, okay? Because your omega can be represented using d theta over dt, so that becomes the second derivative. So you can see yes, we learned a lot of new stuff, but also we didn't really spend a lot of effort because we're building upon something we already know. You can borrow all the equations we had previously and simply change everything to your rotational counterpart, okay? And we were gonna do the same thing when we derive kinematics equations later. Okay, so let's look at a couple questions. Here it will help us understand these concepts. So if I tell you a disk that is spinning at 2 revolutions per second, what is its period? Okay, the period means the total time it takes to complete one round of rotation. The time it takes to go around one time. So how much seconds does it need to go around one time? So that is a question. All right. I will go ahead and let you vote on this. I want you to first take a quick screenshot of the picture. okay? Because I'm going to have to disconnect my my screen and charge up my pen. Hopefully I can write after a few seconds, okay? So take a screenshot and think about this question. And when you're ready, you can start to vote, okay? All right, I'm going to disconnect now, okay? If you're ready, feel free to vote, or if you want to take a moment to think about the question, feel free to do so, okay? Have a couple minutes. Okay, so a few more seconds to put in your vote. Okay, so someone said it keeps giving you error when you try to submit. I assume this is talking about the poll. Don't worry about it. We will try this again and the next poll. And if it keeps coming, having questions, and when we have to figure out what's going on. But for this one, don't worry about it. Okay, all right, good to know. It fixed itself. Okay, very good. Okay, any last minute vote before I close this? Okay, all right, so I'm going to go ahead and end the poll. We can have a discussion. Let's see, this is our results. Okay, so majority chose C, half a second, and there are choices for other ones as well. Okay, very good. So it is asking the time it takes to go one round. Very good, half a second is correct because in 1 second, it goes twice around. 2 revolutions means goes twice around. So if you go once around, it only going to take a half a second, right? So that's your period. That's going to be the period. So when you have a rotation and you start at this position, you come back to the same position, that is called one entire cycle. When you have a pendulum going back and forth, is when you start here, you swing to the other side and you swing back to the same position, that is called one cycle. So the period is decided, is measured from when you start here and when you come all the way back to the same place. So yes, so if you're going one round in 1 second, then you only take half a second to go one rotation. So C is correct. Okay, very good. So that is the period. And that doesn't get into velocity at all, right? Some of you were trying to put a pi in your answer like B. So perhaps you were thinking about velocity. So here is another question. What if I asked you the same information I was given, but instead I asked you, what is the angular velocity? So what would be your answer now? I'm going to go ahead and let you vote again. And to recall, omega is, how omega is decided. When an average velocity is going to be the change of your displacement over time, okay? your displacement change in position over time. Since this is rotating at a constant rate, your average velocity is your velocity at any given point. So it's just one velocity. So you need to translate revolutions into position. One revolution is how much change in terms of its position. So that is what we need to do. Okay. Any last minute vote? Let's go for another 10 seconds, okay? All right, so I'm gonna go ahead and end this. Let's take a look at our results. We're quite split between all these three different choices. So how do we figure out the angular velocity? We start from the definition, right? It's change in position over time, delta theta over delta t. So it's already give us what is the change of position over time. In one time, it goes around 2 times. So when you go around 1 time, what is your change in your position? You have to make sure that we don't write 0 because that does not really capture you're actually moving, right? So you go all the way around, we will describe that you have changed your position for 360 degrees, but we want to represent using radians. So that is 2 pi for 1 round. So in 1 second, you go around 2 times. So that is 2 times 2 pi, right? 2 times 2 pi in 1 second. So which means that is 4 pi radians per second. So that is the answer, right? Which is correctly described by choice C. 4 pi radians per second is the answer. So if people ask you, and then if you take omega and use it to combine with something else to get the units. So for example, later on, we will do omega times r radius. That actually give you a velocity. And you can see in terms of units, radians does not get carried in. We said the radians is a dimensionless quantity. So omega really just give you a 1/2 in terms of units. And r is going to give you meter. So together it gives you meter per second is the final unit set for this omega r combination, okay? So that is something we are going to discuss. You're going to see it later in class. Okay, so now I can write, let's go back to this slides that we created and sort of do a quick summary. So to think about all the counterpart of your quantities, kinematics quantities. So we're doing kinematics. Kinematics has to do with motion, and these quantities help us describe motion. First is position. We do theta to represent its position, and then we have displacement. It is a change in position, that is change delta in r. Change in angular displacement is delta theta. And velocity, you have the velocity average is delta r over delta t. So here, omega average is delta theta over delta t. Now, a lot of times we don't really add a vector on top of our omega. But instead, we will write a little z subscript indicating this rotation is around the z-axis. There is a direction, so there are still vectors. But convention, just people prefer, they don't really add a vector sign on top of omega, but it's still a vector because rotating this way is different from rotating this way, right? So this zero velocity, instantaneous velocity is dr over dt. So likewise, instantaneous omega is d theta over dt. The last one is acceleration. Average acceleration is delta v over delta t. So average angular acceleration is alpha is going to be delta omega over delta t. Again, you can add a z in the subscript indicating it's speeding up in this direction. Okay. Okay, so instantaneous acceleration for the translational motion is dv over dt, and likewise alpha instantaneous is d omega over dt. So you can see you can find the exact counterpart in your rotational case. Are angular quantities vectors? Yes, it is. So the reason we say a z, because instead of saying velocity is counterclockwise rotation or clockwise rotation, we actually say the rotation is in the z direction. I know it's a little weird, but it's decided using this right-hand rule. So using a right-hand rule, okay? So if you have a disk right now spinning clockwise, as indicated in my picture right here, spinning clockwise, right, going this way. So you're going to use your right hand and you're going to let your four fingers curling around in the direction of this rotation. So clockwise, your finger should be pulling around like this. Then the thumb pointing downward, indicating, well, that is what we just established to be the direction of your rotation here. Okay, your rotation is around this axis. So instead of saying omega, instead of saying this disk is rotating clockwise, it is rotating clockwise, but the official direction of that velocity, we call it the negative z direction, pointing down, the negative z direction. That's how we give directions to all these angular quantities. Okay, this is a little bit different from how we do it in translational motion, following right-hand rule. So now let's practice the idea of giving directions to our rotational quantities by looking at a couple of questions. Okay, the first question is, viewed from the top, turntable spins counterclockwise and it is slowing down. So what do we say about the direction of its angular acceleration? This one I'll have you guys discuss it in breakout rooms. So you can go ahead and take a screenshot before you go. Okay? Okay, let's go for 10 more seconds on this question. All right, Gwen, go ahead and close it, okay? And then we can have a discussion. So you can see that your response is pretty much split between A and B. So it's either up or down. Yes, so we're rotating viewed from the top. So it looks like we're doing a rotation in the XY plane. So right, your rotation is either defined as up, which is corresponding to a counterclockwise rotation, or a downward, which is clockwise rotation. So yeah, so how do we decide the direction of an angular acceleration? Anybody would like to tell us about their thoughts? How do we approach this question?
I figured that since the the turntable is slowing down, then therefore it would be opposite to it would be in the opposite direction of whatever direction the turntable is spinning. And since it says it's spinning counterclockwise, then it would be in the angular acceleration vector would be pointing down because counterclockwise normally points up and it's slowing down.
Yes, Tristan, that's exactly very good. That's a very good thought. Because it's slowing down, your angular acceleration needs to be opposing your velocity. Now, if your velocity is trying to spin counterclockwise, then whatever angular acceleration is slowing it down, which it would be in the opposite direction, that's a downward, right? Very good, that's excellent. So your angular acceleration is in the downward direction. Your angular velocity is now in the upward direction. You can see that they're opposite to each other, so therefore it's slowing down, right? We talked about how when acceleration and velocity are in the opposite direction, then the object is slowing down. So that is true for both translational case, also a rotational case. Here's another question. So you're riding on a merry-go-round, traveling forward. The center axis, I'm sorry. The center axis of the merry-go-round is always on your left. So try to picture that in your head. The center of rotation is always on your left. Okay. So can you tell in which way your angular velocity is? So in another way, you can think about in which way you're rotating, this way or this way, and then you can figure out whether that's up or down, right? You can always think about whether it's clockwise or counterclockwise or clockwise, and then you can translate that into the language of it's up or down. So, all right, I'll let you go ahead and vote. I don't believe this one we need too much of a discussion. So just need to picture the rotation in your head. Okay, so 10 more seconds if you have any last minute vote, 10 more seconds. Okay, so let's take a look at your results. And you have almost agreed on A, and that's very good. That is the correct answer. Very good job. So going forward, if you're rotating counterclockwise, you will see that the axis of rotation is always on your left, right? Otherwise, it feels like if you're having a clockwise rotation, going forward, you will see it's always on your right. Okay, so A is exactly correct because an upward direction is what we define to be the direction corresponding to a counterclockwise rotation. Excellent. Okay. So the angular, I have write this a little bit previously when I was talking about the units. So you can relate your angular velocity and translate that into a translational velocity because there are different ways to describe this kind of rotation. For example, think about a point on the rim of the tire, right? A point. If you follow the point, you trace the point, you can tell people, okay, the angular velocity, or you can say the velocity of the point is 2 pi per second. Then people understand. People know that, okay, in 1 second you have gone 2 pi, which is all the way around. Or you can tell people in the language of meters per second. You can say, in 1 second, it has traveled 50 or 0.5 meters, 50 centimeters. So people know that, okay, so how far of a curve that you traveled in a second. So those can be translated back and forth. Right? It's representing the same information, right? So given a angular velocity, how do you translate that into a linear velocity? So for example, if I ask you, what is the speed of the tire rim if the radius is 0.35 meters? And if the tire's rotational velocity is 20 radians per second? It turned out to be simply you multiply the angular velocity by the radius, you get the linear velocity. But how do we derive that? So let's take a look at how the derivation goes. So from this equation is from math, what we know about what would you see in the arc length of the circle. You probably already know that from math. But if you don't know that, there is a quick way that we can derive this ourselves. So let's think about a circle, okay? So let's think about a circle, right? We know that if the circle has a radius r, right, the circumference of the circle is how much? If you go all the way around, what is the circumference of the circle? 2 pi r, right? So which means if you go all the way around, so if I go all the way around, I have gone 2 pi, and the distance I have gone is 2 pi r. So now let's say you didn't go all the way around. You only went for a little bit. So let's say you only went for an angle theta. So what is the distance here? So if theta is 2 pi, then the distance is 2 pi r. But if theta is just a little small angle theta, and what is the arc length? S, we call this, often we call it the arc length, right? Okay, so this is a simple proportional relationship. You can derive the results. You realize, okay, so this is really just telling me S is equal to R times theta, okay? So this is, we have S is R times theta. But in order for this relationship to work, you need to represent your theta in radians. You can't put a degree in there, right? You have to be radians. So by taking a derivative of this relationship, you get velocity, you get a velocity from ds over dt. So take a derivative on both sides. So ds dt is dr theta dt, and r is just the radius, which is a constant. So you can take r outside of your derivative. So it becomes r d theta over dt. So what's ds over dt? That is the speed, linear speed. The theta over dt is your angular speed. If you don't talk about the direction here, right, just angular speed. So v is related to omega by simply multiply that of the radius. So v is radius times omega. So if you want to know what is the speed of this tire rim, you simply using 20 radians per second times the radius is 7 meters per second. So it tells you if you follow this dot in 1 second, it goes for 7 meters. Okay, more interesting questions coming up. For example, so now we want to compare an angular acceleration to another angular acceleration. Let's say you have two bugs. They're sitting at the spinning disk. Okay, Crunchy is sitting at the outer edge, and Buzz is sitting halfway in the disk. So which of these statements best describe their motion? Okay, if you want to compare their linear speed and their angular speed, how do we compare? So I'm going to go ahead and let you discuss on this for a little while. Okay, to compare the angular velocity, uh, you need to think about, okay, in the same amount of time, do you think they have rotated the same amount, right? If one of the bugs go all the way around, do you think the other bug also went all the way around? If you think so, then they do have the same angular velocity. In terms of linear velocity, you need to think about the actual distance they covered. Okay. So hopefully that helps clarify some of these. All right, so let's go for 10 more seconds. If you haven't put in your vote, please do so. Okay, any last minute vote? All right, so now I'm going to go ahead and close this. Okay, so the majority of you think that they have the same angular velocity. So like we said previously, or could they also have the same linear speed? Would both of them be true? So let's think about the angular velocity for now. So if one of them goes all the way around, let's say Crunchy goes all the way around, do you think Buzz also went all the way around? Is that true?
Yes.
Yeah, it is. It is true. They all just went all the way around. They're sitting in the same radius, right? So one goes the way around, the other also does. So they do have the same angular velocity because it's all the same change in position over time. And do they also move with the same linear speed?
No.
Not. So which one will have a bigger linear speed, do you think?
Crunchy would have the bigger linear speed.
Yes, very good. Thank you. So one of them has a bigger radius. So in all the way around, Crunchy covered a longer distance where Buzz covered a much shorter distance, right? So only A is correct. Very good. Now let's look at a different question. So now we have two wheels, and we have seen this on bicycles and some other different equipment or machines. So we have a small wheel and a large wheel, and they're connected by a belt. Now noticing these belts they're not elastic, cannot be stretched. And of course the belt is sort of uniformly going away all around. So the small wheel give you the angular velocity omega, so omega small. So how will we compare the angular velocity of the large wheel to the small wheel? Which one is bigger, smaller, or maybe they're the same? Okay, so this is similar to the bug question, but instead of asking about uh, the linear speed later, this one you probably have to establish the linear speed first and think about the angular speed. So I'm gonna go ahead and let you discuss this for a minute or two, and then you could come back and go. Okay. Okay, let's go for another 10 seconds. So if you have haven't voted already, please do so. Okay, so I'm gonna go ahead and close it, okay? All right, anybody would like to share their thoughts with us? How do we begin to compare the angular velocity of the two wheels, the large and the small?
The problem says that both the small wheel and the large wheel are connected by a belt, which means that both of them have to have the same uh, speed.
Ah, that's a very important note. You're very correct. They're connected by a belt, basically saying they have the same speed, and that's the linear speed. Very good. So they do share something in common that they don't share the angular speed, but they do share the linear speed. Very good. So if you follow the belt, one point, and this belt traveled this much distance in a second, which means it must travel the same distance over here, from here to here. If you follow this, it must also travel the same kind of distance. Otherwise, your belt will be stretched out at some places, right? So they must have the same linear speed. Okay, so linear speed is related to angular speed by the radius. Okay, so if velocity large is the same as velocity small, so omega large times radius large must be omega small times radius small. Because this one, RL is bigger than RS, then which means omega L must be smaller than omega S, right? So you can see that your large wheel has to rotate a little bit slower in order for the small one to catch up, so they can all be connected by the same belt. Excellent, very good. All right, you did very well on these questions. So I think you have understand, all of you, the difference between angle and then linear speed and how to relate and compare them. So again, to summarize what we have done, you can find everything we have talked about looking at the bicycle wheels. So the smaller wheel here and the large wheel here, you can see they always are rotating the same way, right? They have the same angular velocity. But the smaller wheel here and this wheel here, they are connected by the belt and they have the same linear velocity. Okay. So that's why when you pedal here, right, you don't have to pedal a lot, but the small wheel will rotate much, much faster due to your pedaling. And because the big wheel is connected by the small wheel, the big wheel will also rotate that same fast for the small wheel. So, but the big wheel also has a big radius. So as a result of that, you're able to cover a much bigger distance, right? So you're able to simply do some pedaling, but that gives you a big linear speed. That is what we do take advantage of by using the bicycle. Okay, so another thing I wanted to mention is by drawing the linear velocity, the direction. We're here, previously we only looked at linear speed, right? So what is the direction of linear velocity? Well, simply looking at the tangential directions. So for example, here I have 3 different points on the disk, and it's rotating counterclockwise in this way. So you simply drawing the tangential direction to represent the speed of that point. So for example, point A is going downward, but because it's rotating counterclockwise, point C is going upward, and B at that time is going to the left. And you also notice there are different lengths of these vectors because here they're at different distance away from the center. As we said, like Buzz and Crunchy, right? They have a different linear speed because they have the different radius. Okay, so V is omega R. That's why with a different radius, they have a different velocity. So that's why I draw this vector much longer and this vector the shortest, because A is the furthest away from the center and B is the closest away from the center. Okay, lastly, we're gonna use these kinematic quantities relationship to solve some problems. So recall, we're gonna use the same strategy as we did before. We're doing the counterparts from our translational motion to angular motion. all the equation we derived previously, we can use it here. So I'm not going to derive it one more time. I'm just going to show you what they look like, okay? So recall, translational motion, we have this velocity for constant acceleration. Velocity is velocity initial plus acceleration times time. So hopefully you're very familiar with that. So counterparts of velocity become angular velocity. You have an initial angular velocity plus acceleration, angular acceleration times time. Okay, so it's a direct relationship, one-to-one relationship. If you know one, you can write the other. So likewise, the second equation for constant linear acceleration is for the position. The final position is initial position plus initial velocity times time plus 1/2 times acceleration times time squared. Okay, so I can even cover this up. You will know how to write this, right? So it becomes final position is your initial position plus initial velocity times time plus 1/2 angular acceleration times time squared. The third equation, like I said, is not independent of the first two, is a combination of the first two with, you just get rid of the time. So likewise, you can combine these two and get the third equation, and it's exactly similar to what you had previously. Okay. So don't need to memorize them. You just simply need to, if you know one, you know how to write the other. So let's look at this checkpoint question you have already done. So if I tell you there's a wheel, which is initially at rest, starts to turn with a constant angular acceleration. So I know that these equations are useful because it's a constant angular acceleration, right? After 4 seconds, it made 4 complete revolutions. Then how many revolutions will it make after 8 seconds? Okay, so first of all, let's just look at what information can we tell from there? So 4 revolutions seems to be, it's telling us some information about the angular position, right? Because 1 revolution is 2 pi. So, okay, in 4 seconds, the initial position is 0. Let's just call it 0, right? Theta naught plus omega naught t plus 1/2 alpha t squared. We're going to use this equation. Okay, 4 revolutions is 4 times 2 pi. Is the final position, is initial position 0. Initial velocity is also 0 because start from rest. So 1/2 alpha times time is 4 seconds. So here you can find alpha is 16 pi over 16 radians per second squared. Okay. So that's your alpha, angular acceleration. So how much revolutions would it make after 8 seconds? So theta after 8 seconds is again theta naught plus omega naught plus 1/2 alpha t squared. So here everything is the same, right? You can plug in the alpha you just found, but instead you do 8 seconds. So 8 seconds. That's going to be 32 pi, right? So 32 pi is how many rounds? 1 round is 2 pi. So 32 pi is 16 rounds. So it must have gone 16 revolutions after 8 seconds. Okay? So that's how we have used this equation to help us solve a problem. You can see that it's kind of like you didn't do anything new. All these things you have learned before, you can use them again, but it's a new different set of problems you can solve. All of these are rotation. So sometimes instead of just rotating, you do have a centripetal acceleration. Let's make a little distinction to what we did before. The only kind of rotation, sort of rotational motion we did before is the uniform circular motion, and we defined an acceleration called centripetal acceleration. Now that acceleration is, what does this one do? Is only responsible for changing the direction of the speed. direction of the velocity. Okay, but it's not responsible for something speeding up or slowing down. The one that is responsible for something spinning faster and faster or slowing down is this angular acceleration that we're talking about today, is alpha, okay? Is the alpha. So sometimes if you want to combine both of these acceleration together, you call the centripetal acceleration the radial acceleration. Then you call the other acceleration to make it going faster or slower the tangential acceleration. Okay. Just like how linear speed is radius times omega, the tangential acceleration is going to be radius times angular acceleration, alpha. You see that? So it directly is directly coming from this relationship. Okay. So for example, if your alpha is 2 pi radius per second square, then tangential acceleration is 2 pi r radius per second. So what is representing is saying in 1 second you have in 1 second you have increased your speed by 2 pi r radians per second. That is what's representing. Oh, so not radians per second, 2 pi r meters per second squared. Okay. So this is alpha, this is A. So combine the tangential with the centripetal acceleration together. You use radiance acceleration squared plus tangential acceleration squared, square root of them, give you the total acceleration. Okay. So if you're looking at this, might be your tangential acceleration. So you're spinning faster or slower. And this one is your centripetal acceleration. You can see they're perpendicular to each other. When you add them up, you simply just add them up like this relationship right here. Okay, so everything we did one time, we can reuse them by having the same equations as we did previously, these 3 equations. And also likewise, you can see that linear distance is radius times the angle. This one we just derived, remember, by looking at the arc length, S is r theta. So velocity is r times omega by taking the derivative of the first equation with respect to time. This equation, we get it by taking the derivative of this relationship with respect to time, okay? You get this. You can see that the linear and angular, they're all related by an r. Linear and angular related by the radius. The linear and angular, they're all related by a radius r. Okay. All right, one last example, and that's all we're gonna do for today. So we have something like this. You can see it looks like the big and the smaller belt we showed earlier. I have a smaller wheel A with a radius 10 centimeters. It is connected and coupled by belt to wheel B, by the belt B connected wheel C with a radius 25 centimeters. Wheel A increases angular speed from rest at a uniform rate of 1.6 radius per second square. So this one is telling you it has an angular acceleration of alpha of A is 1.6 radians per second square. So that is what this sentence is telling us. So we have to find the time for wheel C to reach a rotational speed of 100 revolutions per minute, assuming the belt doesn't slip. Okay. So A and C are connected. If A and C are connected by belt, they have the same linear speed. So which means velocity A is equal to velocity C. Now linear speed is r omega. A is r omega C. That's why we have this equation. So radius A times acceleration A is radius C times acceleration C. And we're giving all the radius. We're giving the acceleration for A. Now we can quickly find, okay, so what is the angular acceleration for C? So you plug it in, you find the acceleration for C is 0.64 radians per second square, which is smaller than A. That makes sense, right? Because C does not have to speed up as much fast as A. So with this angular acceleration, how much time will take for C to acquire this kind of speed. So here you need to do a unit conversion from revolution. 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So here you need to do a conversion to find the omega for C is about 10.5 radians per second. Okay, so you have speed, now you have acceleration. To find time, you use this equation. Right? Final velocity, initial velocity plus acceleration times time. Okay, so final velocity of C is the initial velocity of C plus acceleration of C times time. Because initially they're all start from 0, right? Then the time it takes is going to be your final velocity over acceleration. So which is the quantity we 10.5 divided by the acceleration we calculated, so about 16 seconds. So you can see that all of this is the same, exactly the same as before. We didn't learn anything new, but we also learned a lot new information by simply doing an analogy between your linear case and your angular case. Okay, so that's all we have for today. That is the kinematics. We did pretty much everything we did do for the first few classes and the first couple of weeks. At the beginning of the semester, we did kinematics, right? We just did everything for rotation. We did it in only one class because everything is similar. It's just for a rotational case. Okay, so starting from Thursday, we will do dynamics. Now the dynamics earlier talking about how forces is related to your motion. So force is equal to m times acceleration. So we're going to find the similar counterparts for our rotation, right? We're going to find, okay, force generate, so here force generate linear acceleration. Here we have angular acceleration. Then what generates angular acceleration? We need to find the rotational counterpart for all of these quantities. Okay, so that is a topic coming up. And after that, we will do conservation laws, just like we did conservation laws for translational motion. All right, so that's all for today. I'll see you guys on Thursday. And just notice that if you haven't done the practice exam, please do so. And I encourage you to try to find more practice problems that you can from your textbook or other sources. And if you have any questions, please let me know, okay? If you have any questions about the exam, feel free to email me, or you can come to the office hours.
Professor, are you gonna have office hours today?
And not today. My office hours are Wednesdays and Thursdays.
Wednesdays and Thursdays? All right, okay. Thank you very much. Have a nice day.
And for the person who asked the question about the homework, the making a correct answer as wrong, if there's something wrong, please email me, okay, so I can fix it. Okay, bye everyone.
Thank you, Professor. Have a good day.
Thank you. Have a good day.
Thank you, Professor.
Thank you. Bye.